All right, Chemistry 3111, or sorry, 3101. What we're going to do today is we're just going to do a short version of Chapter 3, which is the acids and bases chapter. I'm not going to cover every question in here and everything in gross and dirty detail, but I'm going to go over the major points with you, okay? And one of the things that I want you to remember right away, well, I think I have your attention at the very beginning of the class, is let's say we have an equilibrium between a strong acid, like sulfuric acid, right? That's a really strong acid. If we put sulfuric acid in water, okay, water, which is a liquid, there's going to be an equilibrium. And you guys know equilibrium arrows. There's going to be an equilibrium arrow between hydronium, which is going to be the conjugate acid, and the hydrogen sulfate ion, which will be the conjugate base. So to review, this will be our acid, this will be our base, this will be our conjugate acid, and this will be our conjugate base. Now, which side is the equilibrium going to lie to? Okay, well, if I compare the two acids, okay, it turns out that sulfuric acid is a stronger acid. So I'm going to write here stronger acid, and that hydronium is actually a weaker acid, and we're going to quantify that in just a little bit. So the equilibrium is going to lie to the side of the weaker acid. Now, sometimes students will think, oh, well, it should lie to the side of the strong one because it's strong. Well, no, it's going to lie to the side of the weaker acid. Why? Because an acid, if you remember the Bronsted-Lowry definition, is a proton donor. So that means it's going to do its thing. It's going to donate protons. So after it donates a proton to water, what do you end up with? You end up with hydronium. And so that is why the equilibrium is not going to lie to the side of the stronger acid. It's going to lie to the side of the weaker acid. All right. I want you to remember that. Another thing that I want you to remember about this chapter is that it would be wise to memorize table 3.1. So table 3.1, you should, and that's me, that's my nice way of saying you have to memorize table 3.1 because it covers all the pKa's that you need to know for this class. So let's review what a Bronsted-Lowry acid and a base are. An acid is something that donates a proton. A base is something that accepts a proton. So we could say an acid is a proton donor. A base is a proton acceptor. And remember that a proton, right, you guys should remember that a proton is an H plus ion, right? If you think about what a hydrogen atom is, it's got one proton in the nucleus, one electron around it. If you remove that electron, what have you got left over? Just the nucleus, which is a proton. So take a look at this classic example. We have hydrochloric acid plus water gives us a chloride ion plus a hydronium ion. Make sure you remember the name of this ion, hydronium. Hydronium. You would have written that down probably Avogadro's number of times in general chemistry too, the H3O plus ion. So we have our acid, we have our base, right? Our acid is our proton donor, the water is our base, which is a proton acceptor, and we end up with our conjugate base and our conjugate acid. If you're ever struggling to figure out what is the conjugate base and what is the conjugate acid, in that case, I would just think about the reaction in reverse and think about who's accepting a proton. Well, you can see that the chloride is accepting a proton in reverse, so therefore it must be a base because bases are proton acceptors. And you can see that the hydronium ion is donating a proton in reverse, and so therefore it must be the conjugate acid. So again, Bronsted-Lowry definition of an acid and a base. Acid is a proton donor, base is a proton acceptor. Also in general chemistry, you would have covered the Arrhenius definition of an acid and a base, but we don't really use that a whole lot in organic chemistry, so don't stress about that one too much. So again, conjugate acids and conjugate bases. The difference between an acid and its conjugate base and a base its conjugate and its conjugate acid, okay, we can put here the difference between these two. The difference is H plus. One hydrogen ion, one proton is the difference between a base and its conjugate acid and an acid and its conjugate base. So if we take a look at what's happening here, if I put a blue line underneath this anion and a red line underneath water, could anybody tell me, or I'll just ask you this way, I'll say, is the water, in this case, is the water behaving as an acid or a base? Could anybody tell me? Is the water behaving as an acid or a base? In this specific, exactly, it's behaving as an acid, isn't it, right? Because it's donating a proton. You see it goes from water to hydroxide. It lost H plus. So now we can label this is our acid. This is our conjugate base. Okay, because what's left over after your acid loses a proton is its conjugate base. This must be the base. This is called a tert-butoxide ion. This is our base. And this alcohol must be our conjugate acid. There you go. Now, if you're astute, and I know you all are, you probably noticed in this example that water is an acid. And over here, in this example, that water was behaving as a base. So what does that tell you? It tells you that water can behave as an acid or a base depending on the situation. Now, unlike chapter 2, where we talked about resonance, what's happening here is this is an actual chemical reaction that is occurring, okay? There's nothing to do with resonance whatsoever. And so if we draw a curved arrow in an acid-base reaction, we are actually showing the making and breaking of bonds, okay, in a reaction. That's the whole point of a reaction, is that you break bonds and you form bonds. So now, if we use curved arrows to represent the flow of electron density, we see our base, which is our proton acceptor, accepting a proton from our acid, which is again our proton donor, and what's left over, we get our conjugate acid, and now we have our conjugate base, okay? Now, I don't think it's wise to try to memorize how the arrows work. You guys know that the tail of an arrow has to start on a bond or a lone pair. You see that the tail of this arrow ends up on a lone pair. The head of the arrow should end up on a nucleus somewhere. So we end up taking the proton. So we say it attacks the acid. And then you see that sorry about that. One of those days, I guess. Okay, I think everybody can see my screen now. Okay, so these curved arrows represent the actual flow of electrons in a reaction. Okay, they're the same kind of curved arrows that we used with resonance, but here they're actually showing the physical movement of electrons. And so learning how to draw mechanisms like this one, okay, drawing mechanisms is one of the most valuable skills in all of organic chemistry. And so it's imperative that you learn how to draw mechanisms. You have to practice this using a pencil and a paper. You've got to do it that way. You might think, well, the ACS exam or an MCAT, that's all multiple choice. I can just kind of study it by looking at it. Impossible. Okay. You're like, well, that's a bold statement. It's right. Okay. It's impossible to learn it without trying it. Okay. So here's a specific example. We have hydroxide, which is a strong base. You would remember that from general chemistry. This is a carboxylic acid. You should recognize the functional group. The base is the proton acceptor. The acid is the proton donor. In this case, water is our conjugate acid. And this is called the acetate ion over here, conjugate base of acetic acid. But anyhow, I'll just draw that in there because you would have seen that in buffers in general chemistry too. But anyhow, there's our conjugate base. So what's some of the vernacular that we use? We say the base attacks the acid. You heard me say that a couple of minutes ago using a pair of electrons. And it says the acid cannot lose a proton without a base taking it. Okay? You got to remember this. If you have an acid donating a proton, there has to be a base accepting it. Okay, an acid cannot just donate its proton into the middle of nothing. So when you have your mechanism, like is shown here, it says the mechanism shows two arrows indicating that two pairs of electrons are moving simultaneously, right? This is a bond being formed. So bond being formed is what's being represented by this curved arrow, and this one represents a bond being broken. Okay, bond being broken. And you can see that this pair of electrons in that bond end up as a lone pair on the oxygen in the end. All right, so let's see if we can draw some curved arrows for this one. This molecule here is called phenol. So phenol, you don't have to know the name of that compound. It's just a cool thing to know. This is water over here. You obviously know that. You also know the hydroxide ion. So hydroxide ion. And this is called a phenolate. Okay, if you think about chemistry, when something ends in ate, it usually has a negative charge. So we have our hydroxide, which is going to be our base. And you can tell that because the hydroxide goes from being OH minus to H2O, right? It gained a proton. And you can see that the phenol must be the acid because it loses its proton, all right? So I filled in the lone pairs on the hydroxide. I didn't do a very good job at the bottom. But there we go. I'm going to fill in the lone pairs on the phenolate too. Put the lone pairs on the water. Let's just put in all the lone pairs. All right, there we go. So now what's going to happen is the base is going to attack the acid. So remember, we're going to form a bond between oxygen and hydrogen. So how do we do that? We're going to take a lone pair and we're going to pick up that proton. Okay, so now we've made a bond between the oxygen of the hydroxide and that proton that the head of the arrow is ending on. And now we have to break this bond because hydrogen cannot have two bonds. So we're going to break this bond and we're going to put the lone pair on here. And that makes sense because here we started with two lone pairs and now we have three lone pairs. So there's our acid-base curved arrows. And again, this represents an actual chemical reaction. Now, if we label our acid and base, the phenol is our proton donor, it's our acid, hydroxide is our base. And if you think about the reaction in reverse, the phenolate would be accepting a proton, so it must be the conjugate base, or you could say what's left over after the acid donates a proton is the conjugate base. And then we see that water is our conjugate acid. Water is our conjugate acid, like that. There you go. Now remember, this is an actual reaction. Chapter 2, when we look at curved arrows, we're just showing the delocalization of electrons. We're not showing any reactions whatsoever. Now, how do we quantify acidity? You would have looked at a lot of equilibria in chemistry 1411. If you go back to, if you took chemistry, general chemistry 2 at UCCS, it's called chemistry 1411, and you would have covered things like, who remembers Ka? First, you would have started with K equilibrium, then you would have studied Ka, Kb, you even studied Ksp. Does anybody give me a thumbs up if you remember seeing those things in general chemistry 2? Equilibrium constants, right? You're like, they never went away. We did like 3 chapters on them. Absolutely. It's a huge part of that class. So it's back, but what we're going to focus on in organic chemistry is going to be Ka, the dissociation constant for an acid dissolved in water. Anyhow, and this is just how we put a number, how we quantify acid strength, okay? And remember, the lower the pKa, so we'll just write this in here, lower pKa equals stronger acid, stronger acid. And if you want to write in, you could write in higher pKa equals weaker acid. So let's take a look at where Ka comes from. And again, this is review from General Chemistry 2. If we put an acid, this is just some kind of generic acid. It's got a proton that it's ready to donate. So if it donates a proton to water, you end up with the conjugate base plus the conjugate acid. When you write out a K equilibrium expression, you say it's equal to the concentration of the products, the product of the concentration of the products divided by the product of the concentration of the reactants. Now, the difference between K equilibrium and Ka is that we eliminate H2O. Okay, we get rid of that and then it turns into Ka. It's the reason we can do that is because the concentration of water is constant, so you don't have to worry about the concentration of water. Anyhow, but now we get the Ka is equal to the concentration of each of the products, okay, and their product divided by the concentration of the weak acid. Remember that these square brackets represent concentration in moles per liter. All right, so it says if the acid is strong, will the Ka be bigger than 1 or smaller than 1? Can anybody answer that? If your acid is strong, will it have a big Ka or a little Ka? We're not talking about pKa, we're just talking about Ka. If your acid is strong, would you have a big Ka? You'd have a huge Ka, right? Exactly. Why? Because remember, the purpose of an acid is to donate protons, right? To convert it into hydronium. And so if it does its thing, it's going to push the equilibrium to this side, right? So we could put like this if it's a strong acid. So that means you're going to have mostly products and only a little bit of reactant. So you're going to have a big number in your numerator and a small number in your denominator. And so the answer is going to be, if the acid is strong, you're going to have a Ka bigger than 1, a big Ka. Okay, remember, pKa is something different. So now, it says here that Kas can actually take on a huge range of values, all the way from 10 to the negative 50 for really weak acids to 10 to the power of 10 for really strong acids, okay? So, I mean, we're talking about 10 to the power of 60 difference in order of magnitude. It's really hard to work with huge numbers and really, really small numbers. And so what do? Is we take the negative log of Ka, and that just allows us to focus on the exponent, okay? But it flips the negative sign. The negative becomes a positive and vice versa. And so now our pKa's, which is the negative log of Ka, if you remember, you know, pH is equal to the negative log of the concentration of hydronium, right? That's something you would have learned in general chemistry. pKa is just the negative log of Ka, okay? So now we get pKa values that range from negative 10 to 50. And so if you have a really low negative number, like negative 10, that's going to be a strong acid, okay? And if you have something with 10 to the power of 50, that's going to be a very weak acid. I'm talking like the weakest of the weakest. I mean, it's not a proton donor whatsoever, okay? So there you go. So low number or low pKa is going to be a strong acid. High pKa is going to be a weaker acid. Remember, you have to know the difference between Ka and pKa, but in organic chemistry, I'll just level with you. We're going to focus on pKa, okay, 99% of the time. So again, I recommend that you memorize the table of acids. So this is one that I took from a previous version of the textbook. But again, like I told you on the first slide, you've got to memorize the values from table 3.1. Everybody has to do it. I had to do it. You're going to do it. It's going to be great, okay? And the reason why you want to do that is because if you memorize this table, so I'll just write here on for you, memorize this table, it's going to get you out of so many jams in organic chemistry. It's basically like having a mini answer guide in your head, okay? Get all the solutions to everything in the chapter if you can memorize this table. And I'm going to walk through it with you really quickly. But if you look at the order of magnitude, okay, if you go from -9, let's say, to -7, if you compare the strength of sulfuric acid and hydrochloric acid, they're both strong acids, right? They're both dangerous. I wouldn't want to get either of them on my skin. But the difference between -7 and -9 is 2, right? So how many times stronger of an acid is sulfuric than hydrochloric? It's 2 is the difference between the two, right? If you have -9, subtract -7, you get, well, actually, if you take -7, subtract -9, I guess you'd get +2. But it's 10 to the power of 2, which is 100. And so sulfuric acid is not 2 times stronger, it's 100 times stronger, okay? That's how logarithms work. So now let's take a quick journey through this table, okay? We start out with the strongest of all the acids that we really look at in this class, which is sulfuric acid. Now, I know that a lot of you might be interested in other crazy strong acids that you saw on the internet or something. Are there acids stronger than sulfuric acid? Of course, yes, absolutely. Do we worry about them in this class? Not really, so I'm not going to spend a lot of time on that. But sulfuric is one of the strongest acids that you see, okay? So this is the acid, and the hydrogen sulfate ion would be its conjugate base. Now, hopefully you remember the trend from general chemistry that the stronger the acid, the weaker its conjugate base. The weaker the acid, the stronger its conjugate base. So we go from sulfuric acid, which you should all know the name of. Then this one here, this is called an oxonium ion. It's a protonated carbonyl is what it is. And you can see it's missing a lone pair on here. But the reason, if you're like, why is that in there? Okay, it's in there because we see it a lot in mechanisms that we look at in the class. But it's really acidic. It's -7. It's even the same order of magnitude as hydrochloric acid. So it's a very strong proton donor. The next one is hydronium. Okay, hydronium, it says -1.74. As long as you know -2, it's good enough. And also, anything that has a pKa below 0, okay, anything below 0, I would say is a strong acid. So strong acids, anything with a pKa below 0. Now we get up into carboxylic acid. Okay, a carboxylic acid, this is acetic acid here, but either way, this is a carboxylic acid. I mean, it says 4.75, as long as you know 5, approximately, okay? That's good enough. The next one is, this is called a 1,3-dicarbonyl, 1,3-dicarbonyl. We don't see this a lot in this class. You need to know that it's 9. but you see it a lot more in organic chemistry too. And you should be able to draw all the resonance forms of this. Moving on from there, hey, you recognize this guy? I just talked about it a few minutes ago. This is phenol. Okay, phenol has a pK of 10. So not, it says 9.9, but 10 is going to get you anywhere you want to go. Water, 15.7. You notice that this is ethanol. So this is ethyl alcohol or ethanol. And this is called T-butanol. Actually, I'll name it more. It's called tert-butanol. What you really need to know is that alcohols kind of range between 16 to 18. So 16 to 18 is going to, again, it's going to work for anything you need to do in this class. The next one is a ketone. This is acetone, yes, but this is a ketone. A ketone is 19. The next one is really important, okay? This is a bond between an sp hybridized carbon and a hydrogen. It's 25, okay? It's pretty acidic compared to something like an alkane. Then we come up to, this is ammonia, but you could put here ammonia slash an amine. Any kind of amine is going to have a high pKa. It's going to be around 38, something like that. So it's quite basic. Then you have a bond between an sp2 hybridized carbon and a hydrogen, which is around 44. So now we're into the weakest of the acids. And then you have a bond between an sp3. This is the most ubiquitous bond in all of organic chemistry, is a bond between an sp3 hybridized carbon and a hydrogen, which is not acidic at all. But again, if you look at the conjugate base of an alkane, it's one of the strongest bases that there is. Okay, it's a very, very strong base. Okay, so what are some strategies for memorizing things? I don't know, staring at it, I guess. You could make a flashcard. You could, I like to just practice. I like to write things out with blanks on it and then try to fill in the blanks. That works for me. But either way, you want to memorize all the pKa's in here. Now, again, remember, you would have covered this in general chemistry, is that the stronger the acid, the weaker its conjugate base, and vice versa. The weaker the acid, the stronger its conjugate base. And so if we look at the conjugate base of something like sulfuric acid, this is so weak, it's not gonna, it's like, I don't care about protons, I don't want to pick up a proton. But then if you look at the conjugate base of the weakest acids, an alkane, this thing is so strong, it will pull a proton off of just about anything, okay? Excuse me. All right, so there you go, a little bit about acids and bases. So let's see if we can take a look at this molecule as a beta blocker, propranolol. It's used to treat it's an antihypertensive agent, so it's used to treat hypertension or high blood pressure. It says identify the most acidic proton in the compound. Now, before you get into it, we're like, oh no, I have to look at every proton in the universe. Well, not really, okay? There's not that many types of protons in here. You have protons between sp3 hybridized carbons and hydrogen, like this one, or, you know, on this carbon, or on this carbon, or right? These are all sp3 hybridized carbons that I'm circling here. There's no other ones. So the pK of this is going to be around 50. Okay. Now, if you look at, you know, say this proton, for example, that's attached to an aromatic ring, but this is an sp2 hybridized carbon. And so if you go back here to the table, it said if you have a bond between an sp2 hybridized carbon and a hydrogen, it's 44. It turns out that the pK of a proton attached to an aromatic ring is 43, but that's close enough to answer the question. We won't have any problem with that. So I'll just put here, I'll just put 44 is fine. It's going to work just fine, okay? So this is sp2, this is sp2, there's no proton there. This is sp2, this is sp2, this is sp2, this is sp2. Okay, so we've got those two. Now we have a proton on our alcohol. And if you remember, the range of a proton on an alcohol was somewhere between 16 and 18. And then we had a proton on an amine, and I'll just circle this in here. And what did it say the pK of the proton of an amine or ammonia was? The pK was around 38, okay? So it's abundantly clear that the most acidic proton on here is the proton on the hydroxyl group. It's around 16 to 18. So there you go. That's our most acidic proton. And so if you're wondering, you know, what's the consequence of all this, okay? It's that an organic chemist has to be able to look at a molecule like propranolol and make a judgment call pretty quickly and say, okay, well, this is by far the most acidic proton by what, like 20 orders of 10 to the power of 20. So if you were to treat this compound with a base, which proton is going to get removed? It's going to be this proton before anything else gets taken off, okay? So that's a little bit about this question. Now, in the next one, what we're doing is we're trying to look at these two bases and figure out which one is a stronger base. So we've got the conjugate base of an alkyne and the conjugate base of ammonia. Now, what's the rationale we're going to use? We're going to say whichever one produces a weaker acid is going to be the stronger base. So what we'll do is we'll look at the conjugate acid of both of these. So I want to take a short break. In a couple of let's take a short break, and I want you to try both of these and to see if you can evaluate which one of these is the stronger base in both of these cases.